Hello, and it's October 30th. It's Friday, and here at school, this is the Senior Citizen Day, and I'm hoping lots of kids dress up. I am definitely dressed up. This is going to be Unit 4-1, and it's going to talk about the basic continental margin types, as well as some of the ocean features that we'll talk about. But basically, if you take a look, I've shown you this picture before. We're going to be talking about the dark blue stuff and the light blue stuff, and the fact that we got dark blue stuff sitting out, and we've got this island out there, and we've got these islands out here, which are all volcanic. But this basically is the marine provinces. It's the different depths and conditions that we find out in the ocean. If you take a look at the ocean versus the land, you can see we actually have this is 10 to the millionth kilometers squared, 10 to the millionth kilometers squared. We have 361, got 93 million kilometers, which are the dark blue, and we have 268, which is the light blue, for a total of 361 versus continents, 147, and volcanic islands, 2 million kilometers for a total of 149, and that makes up almost 71% and almost 29% of the Earth's surface. So marine provinces. Here's a picture of the continental margin, and you can actually see this blue stuff right here. That's what they're showing you. It's actually part of the continental rock. It's felsic, it's granitic, it's 2.7 grams per cubic centimeter. And then the light blue stuff, except for some of the stuff that sticks up, the light blue stuff is oceanic, mafic, 3.1 gram per cubic centimeter, along with continental material sitting on top. On dust, we got the mid-ocean ridge, the divergent area, which is the new crust, and very little sediment, and the sediment gets thicker as we go, primarily because it's older, but also because it's closer to the parts that are actually getting weathered and eroded. These little things actually give rise, or given rise to by normal faulting. This was ripped apart. These two continents were together right here, and the divergence ripped them apart. It caused normal faulting, which basically means that the hanging wall, if you imagine yourself standing right there, this is the wall that stands above you, is falling down, and that is a normal ocean. You get the exact opposite, where this one gets pushed up, if we're actually colliding these things rather than ripping them apart. And again, the asthenosphere is what leaks out at the mid-ocean ridge to produce that oceanic crust, which we'll talk about in this section. Bathymetric techniques. We started actually taking depth soundings using ropes, and we would actually drop the rope with a rock on it, and we would drop it down. The rope had marks on the sides of it, so we could actually tell how far it went down. And when the rock hit a surface, we actually felt the weight of the rock change, and that was the depth of the water. Then we'd move the boat and do that, and we could actually do a long line and then make a map of the ocean floor. This was usually happened really close to the surface, because what happened if the deeper water is this rope got so heavy that it was heavier than the rock, and you really couldn't tell whether the rock was there. So then we switched over to wire. You could actually go down to deeper depths, but then we're trying to go down 7 miles of wire for the deepest depth down the Marianas Trench was a problem. Here's a picture of a sailboat. Looks like a military boat with all the cannons, and you can see the people are dropping ropes down the side, and it actually is affected by the boat going up and down. It's affected by lots of things. Now our new techniques actually take an effect of all that. It sounds like I just got an email. I'm doing this one at school rather than home. Echo sounders use sound waves, and then it's reflection, so it actually goes down and comes back up. So if it went down for 100 meters and came back up for 100 meters, it actually traveled, at this speed, 1,500 meters per second, but it basically went down and came back up, and that's not the depth of the water. The depth of the water is actually half of that. So 1,500 meters per second, and if it's not on your packet, you should write that down. We've gotten very precise in our depth recording, and we actually now make continuous profiles, sweeps of the ocean, so we get a really good 3D image of the ocean floor. Computers have helped out a lot. We can even use seismic profiling, which will actually show the subfloor, and I'll show you pictures of these things. And we can use multi-beam echo sounders, which actually use different wavelengths of sound, and which actually gives us a much better high resolution picture, and we can use what's called size scan. So if the boat's right here, it doesn't just look straight down, it actually looks over a wide swath. And then we can also now use satellites. Here's an example of side scan sonar. This one is actually called Gloria, and it's actually can move up to 10 knots speed. It's an 8-meter long thing. We drop it 50 meters down, so it's much farther below the boat. And what it does, it sends out sound waves, and it actually looks to the side and scans. And you can see this is actually a 60-kilometer path, so it can do a pretty good swath. And if you could go from the Atlantic coast of the United States all the way over to Africa or Europe and just do a 60-kilometer swath, that's a pretty good chunk of the ocean. Then just move and make the next swath over there and the next one over there. And if two boats did it, one could go south as the other one goes north. But again, it's going at 1,500 meters per second. I may actually show this in class. You can take a look at it if you want to. Although I'm not going to load this PowerPoint because I really do want you to watch these videos. Seismic profiling, what we do is we take the boat and we put a receiver, very much like Gloria was, lower, and then we actually drop depth charges, and the charges explode, and they send out sound waves which bounce off the surface, bounces off layers of the rock, and actually can tell us. And there's another divergent zone where if you were standing right there, the fault above you, the hanging wall, slides down, and that's from Divergent. So we can actually see the different layers that are in the rock. We can do this for oil exploration down at the bottom of the ocean as well. And again, these waves travel at 1,500 meters per second. Here's a YouTube video which actually explains the seismic profiling, and again, I'm not going to show that because that would add 4.5 minutes to the video. Satellite measurements. If you take a look at these mountains, the mountains actually cause distances farther from the center of the earth, and that decreases gravity. If you want to lose weight, just climb a mountain. And what that does, it allows the water level to go up. So if this thing goes up 2,000 meters, you may get a water change of about 3 feet, and that's an ambient. We've got waves going over all this stuff, but satellites can make very, very minute changes in sea level, and we actually look for these little blobs of water, and we can actually see what's going down. And the valleys actually is, we do get crests and troughs in the water, sea level, just like we get it down below. We are going to do a web assignment, and I'll explain that in class, but once you bring these notes in, we'll do that web assignment. Hypsographic curve, which I showed you in Unit 1, and all this basically does is it shows us that there's much less land sticking above sea level as there is below, which means there's less land on the surface of the earth than there is water. If I was to completely smooth out the land, we'd end up with an average height of about 840 meters. If we completely smoothed out the water, we'd end up with a depth of about 3729. They're actually saying it's 3,800 meters. That's actually below, so they're giving you a negative number. And if you were to smooth out the entire planet, you'd end up with water over the entire surface, and that would actually give you an ocean that's 2,686 meters, and that's called the Earth's sphere depth. So if you actually smoothed out the Earth and made it into a perfect sphere, you'd have an ocean sitting over the entire planet of about 3,700 meters. Continental margins. The margins of the continents do extend underneath the present sea level. If we have another ice age, the water will actually move away and we'll actually get much more coastline. If the ice melts, it'll, and this is called transgression, it would egress back over the coastline. It would actually climb up the sides of these volcanoes, and if we talk about coral reefs, if they can't keep up with it, it would actually extinguish the coral reefs, and very small sea level islands will be underwater. Continental margins are shallow areas close to land. They're underlain by continental crust. Remember, that's felsic, 2.7 grams per cubic centimeter. Felsic means feldspar, but it's basically a silicon type, only silicon type crust. And it's classified as either being a passive or active margin. Passive if it has no subduction, which forces rock down and melts and causes volcanoes. This is a passive margin. The east coast of the United States is a passive margin. The west coast is actually what's called an active margin. Passive margins, presently no plate tectonic boundary, and the reason that's true is because they used to sit over this divergent area and they've moved, and there's no subduction, no rock being pushed where it does not want to go. It's tectonically active at one point, because we can see the volcanics in the Appalachian Mountains, but it's not tectonically active now. It does have a very wide continental shelf. It has a continental slope, and it even has a continental rise, and the continental rise usually is made up of the sediment that's washed off the shelf or the continent and washed off the shelf on down the slope and accumulated down here, and we'll talk more about these later. Active margins have very that is it's a plate boundary, it is tectonically active, and it's a modified coast feature because we get lots of changes, and it's classified by the type of plate boundary. Remember, we can have an oceanic plate coming together like they are in this one, creating what's called an island arc, and we can actually have an oceanic continental coming together, and we can have a volcanic arc, and I'm not sure why they call that a volcanic arc. Continental margin profile, very wide continental shelf that are passive. They've got a slope, and you got a rise, and you have abyssal plain, and the abyssal plain is 4,000 meters deep, so it's actually a pretty deep ocean. Active tend to have smaller shelves. They tend to be a little bit more steep. They do have a slope which goes down to the trench, and the trench can be like the Marianas Trench, about 7 miles, which is about 11.5 kilometers deep. But again, the abyssal plain is like that. And if you take a look, this is the passive margin, no plate tectonics, no volcanism. This is the active margin, and you have a rift valley usually in between, which is pushing these puppies away. And this one's actually moving towards the left as this plate is moving away from here toward the right, which makes this oceanic crust subduct down underneath. And I can't tell if this is an island or if it's a continent, but these are probably continents on both sides. Active margins, you can have oceanic, continental. These are convergent, and it is at a plate margin boundary. Narrow continental shelf. Here's an example of a volcanic arc. This is more of an island arc. You do have the trench. You do get this accumulation of material on both sides, but it actually gets pushed this direction and gets accumulated more on this side, and it's called an accretion wedge. You do get the trench, you do get subduction, you get the rock that wants to be up here melting, and it comes back up, pops through the crust, producing a larger area which could actually stick up out of sea level and create islands. Steep continental slope, oceanic trench, deep ocean trench. It does have also a convex volcano. As the thing goes down, it actually produces a concave plate, and it actually makes a concave or a convex, depending if you're looking at this side or this side, but the side closer to the trench is actually a convex line of volcanoes, islands if it's an oceanic, and volcanic arc if it's an oceanic continental. Here's the Bering Sea, and you can see this beautiful island set just like this. So we actually do have a deep ocean trench right here. So the trench goes down and produces these, and they're all over. You take a look at Japan, look at the Philippines, look at lots of other places, and it's like that. Transform active margins. This is actually a divergent area, and we do get transform faults. Divergence when they move away from each other in opposite directions, transform when they actually move opposite directions side by side, and we get the fracture zones, which we learned about in plate tectonics. An example of that is right here for the Canary Islands. So transform plate boundaries, they usually make either linear islands or they make banks, areas that are still below sea level, but cause shallow water, and fishermen will look for that. There's an animation of that, and okay, it's not going to ask me, it must not be a shockwave. So here's the divergent, the Rift Valley, mid-ocean ridge, and you can see the plates are actually moving away from each other, so between X and Y you do get this transform boundary, and you can get islands and banks from this. And then the fracture zone is when the two plates are moving, so past Y or past X, or actually on opposite ends of these red lines. And I think that's a deep basin. These are usually close to shore. And I think that's the end of 4.1. Okay, thank you for stopping by. Appreciate it. And that's not what I wanted to do. I just wanted to escape. And I want to go back into here so I can shut it off. And that's 15:15. Thank you.